Hello, my name is David Valdés, and today I wanted to talk to you about factoring special forms. We could call it even factoring specific forms. Really, what makes these things special is that every one of these factors into the same thing every time. Every one of these has a general form, and so I guess that's why we call them special, but again, we could also call them specific. So that being said, let me just give you a general map of what all these guys look like, and then I'll go into each one of them in detail. You'll notice that this one has a little asterisk by the sum of squares, and that's because the sum of squares factors into something having complex numbers, which include an imaginary unit. So if your course uses an imaginary number, then you're going to want to factor the sum of squares if your task is to factor. If your course does not use the imaginary unit, then I wouldn't worry about it. I would leave the sum of squares as is whenever you come across factoring that, and you can just say it does not have real factors. Okay, it's not that it doesn't factor, but it doesn't have real factors. So let me show you the map I was talking about, and then we'll get into specific videos on each one of these. So the first one, the difference of squares, looks like a squared minus b squared, which makes perfect sense, the difference of squares. That always factors to a minus b times a plus b. The sum of squares looks like a squared plus b squared, and this does not contain real factors, but it does factor into the following two binomials that have a complex component. So here's what this looks like. A plus bi times a minus bi, where I squared is equal to -1. And that I, that's the imaginary unit. We can define I as equal to the square root of -1, or we can say I squared is equal to -1. And when you do that, with that definition, then you can say this factors to a plus bi times a minus bi. The perfect square trinomial is really a trinomial that factors to a perfect square. And there are two cases of this, and I'm going to write down both cases in one line and explain how I'm writing it down. So first, let me start with the trinomial. That looks like a squared plus minus 2ab plus b squared. And the plus means if we have a trinomial with a positive, we have the plus. If we have a trinomial with a negative number, then we have a minus. Okay? This always factors to a plus minus b quantity squared. So again, if you have a trinomial that has the positive number here in the middle, then you use the positive case over here, or put a plus between these two guys. If you have a minus in the trinomial, then a minus shows up here in the binomial. This represents two different cases, and I will show those two cases when I talk about the perfect square trinomial in more detail. The sum and difference of cubes has, I can write it in one line. It's two different cases. One is the sum of cubes, one is the difference of cubes. And so, kind of like I did there, this is what that looks like. A cubed plus minus b cubed is equal to, parentheses, a plus minus b quantity, and then new set of parentheses, a squared. Now these signs flip to minus plus ab plus b squared in the end. So the way this map works is if you have the sum of cubes, the plus, then this first binomial has a plus, but then when you get to this trinomial, you got to put a minus here. Okay? If you start with a minus, then you have a minus here, but then you switch to a plus in the trinomial, and the last guy is always a plus. And so, again, I'm going to separate this into its two different cases when I talk about the sum and difference of cubes in particular. So let's move on and start taking a look at examples of these specific items.